So we are taking data structure and algorithm question and answers. Now let us see, draw the expression tree of the following infix expression. This is an infix expression, and first we have to draw the expression tree, and then we need to convert it to prefix and postfix expressions. So this is the expression tree of this expression, and if you want to convert it into the prefix and postfix, you know what prefix is, what postfix is, that is Polish and reverse Polish notation. So the postfix is this of a plus b plus c into d plus e plus f into g plus h. Let us see how we do it. First is we take the bracket one, ab, so ab plus, then de, that is de plus, then gh plus. Okay, once this is done, ab plus will remain here. Now we are confronted with de, this bracket, and c. So this has to be multiplied, so we take it in bracket and we multiply it and keep it on the right side, that is the postfix. Now we have this expression and this expression, because multiply has greater precedence than the plus, so we'll apply this, that is a, this cd plus f, and then multiply with d. Okay, no, let me tell you again, let me change my statement, because this is in bracket. Okay, this is in bracket, so we'll do for plus first. So what we are going to do is we'll apply this with this, because this is we'll apply this plus first, then we go to the right, that is left to right associative is plus. So ab plus cd plus star means multiplication plus, and now we are left with f and this expression. We'll, because this is in bracket, we'll apply it, whole of this, then f, then plus, like this. Now these are two expressions and we have to multiply, so these two expressions like this, here, and then multiplication. This is the postfix expression, and in the same way we can make the prefix expression. These are the steps. So this is the final prefix expression, that is we have one Polish and one reverse Polish expression for this expression. Next question is implement a queue using a single linked list. How you can implement a queue? The operation insert and delete should still take order of one time. Now this is very important. Insertion and deletion, that means in a single linked list, if you want to insert, we have to traverse. That is, we have to traverse. So at least some if insertion has to be done at the end, so the end comparison has to be made, but it is saying that only order of one needs to be done. Delete also we have to reach to that node, and then we have to delete. So let us see how we can implement a queue using a single linked list. So while implementing a queue as a single linked list, a queue consists of a list and two pointers, q dot front and q dot rear. So we insert an element like this. First we get a node, then we have info and next part. So info will be x, null for the next, means for the initial, and if we see that the rear part is equal to null, then we assign this p to the front. Otherwise we assign this p to the next of q rear, and then we assign p to q rear. So if q front and q rear, these are two pointers to represent front and rear, this is how insert will be done. And the deletion would be something like this: if empty, that is, if the empty is q, the q is having no element, how you can delete it? So if q is empty, then we represent q overflow. Otherwise we assign q front to p and the information part to x, and the next of p to q front. And if this q front is null, we assign null to q rear, and we free that node and we return x. This is the way we can implement a queue using a single linked list. Explain how to implement two stacks in one array. Two stacks in one array in such a way that neither stack overflows unless the total number of elements in both stacks together is n. The push and pop operation should run in constant time. So let us see how we can make it, because the operation should run in order of one time. It is like this: two stack S1 and S2, which can be implemented in one array. So this is our array. The first array, basically it is one array only from 1 to n. But here the two stack S1 and S2, which can be represented like this. We define A1 as the bottom of the stack S1, this stack, and we assume or we let this S1 grow to the right, means we allow this to grow to the right, and we define AN as the bottom of the stack S2 and allow S2 to grow to the left this way. So in this case, overflow will occur only when S1 and S2 have more than elements together. So this technique will usually decrease the number of times overflow occurs. So there will be separate push pop operation which can be defined on S1 and S2. Next is two binary trees are similar if they are both empty or if they are both non-empty. And left and right subtrees are similar. Write an algorithm to determine if two binary trees are similar. Let us see. Two binary trees are similar if they are both empty or if they have both non-empty and left and right subtrees which are similar. So this is the code. We assume two trees, tree 1 and tree 1. The algorithm would be something like this. We have tree 1, tree 2. So while tree 1 is not equal to null, tree 2 is not equal to and this is the AND one, AND operator. If because we have to see that whether they are empty left or right. So tree 1 root is equal to tree 2. Then we apply or we call this similar again for left of tree 1 and left of tree 2. Then we again call recursively this similar for tree 1 right and tree 2 right. Otherwise, if tree root is tree 1 root is not equal to tree 2 node, okay, then we say that the trees are not equal. See, this will be tree 1. So this is the simple algorithm to find if the two binary trees are similar or not. The degree of a node is the number of children it has. Show that in any binary tree, the number of leaves are one more than the number of nodes of degree 2. How can you make it? Let us assume that n be the number of nodes of degree 2 in a binary tree. So we need to show that the number of leaves in tree is n plus 1, that is 1 more than the number of nodes of degree 2. So when n equal to 1, the result is obviously true. When you have, because if node is 1, then the leaves are 2. It is a binary tree. 1 plus 1. Let the formula is true for n equal to k. We are doing it with the principle of induction. If there are n nodes of degree 2 in T, then T has k plus 1 trees. So if this is just by the principle of induction, we have taken the basis of basic. Now if we add 2 children to one of the leaf node, the number of nodes in degree 2 will be k plus 1 and the number of leaf node will be k plus 1 minus 1 plus 2. That will be k plus 1 plus 1. So it becomes k plus 1 to k plus 1 to k plus 1 plus 1. So we conclude by induction that if a binary tree has n nodes of degree 2, it has n plus 1 leaves. Write the non-recursive algorithm to traverse a tree in pre-order. So how to traverse in pre-order? The non-recursive algorithm for pre-order traversal, it will be, first we will initially push null onto the stack. Into the stack we'll push the null here, okay, and we set pointer to ptr to root and repeat the following step until pointer becomes null. Pre-order down the left most path routed at ptr. So we have to take the pre-order, so we have to go to the leftmost. Process each node n on the path and push each right child, if any, onto the stack here. The traversing stop when the pointer becomes null again. Then we do the backtracking. We pop and assign to ptr the top on the stack. And if ptr is not equal to null, then we return to step 1. Otherwise we exit. So this is how we use stack to put elements and then we can reverse it or retrieve it. Okay. Give the adjacency matrix of the following graph. How you can find out the adjacency matrix? This is the graph. We have seen the questions how can we do it? So this will be done like this. Please, you have to give time to this graph to understand. The adjacency matrix would be something like this. There are how many nodes first of all? A, B, C, D, E, F, G, H, I. So in all, there are 9 nodes. What is this exactly? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 by 9 matrix we have to make. So it will be 81 entries. And the entries will be like this. Let me tell you about A and one more. So let us start with A. A with A will be 0 because it will be a self path that will not be counted here. Now A to B is there, so we place 1 here. Otherwise A to A is 0. Then there is no other path from A to anywhere. So all will be zeros. Let me take some others. Say D. D has a path from to C. So with all others will be 0. These two. C will be 1. D has a path to E. So the entry will be 1 with D and E. The rest all will be 0. So this is how we make the adjacency matrix of the given graph, which is like this. I hope you will complete it by yourself. Draw the complete undirected graphs on 1, 2, and 3, 4, and 5 vertices. Prove that the number of edges in an n vertex complete graph is n minus 1 by 2. So let us start. We have one vertex. We draw the complete directed graphs on 1. And we have to prove that the number of edges in an n vertex, the number of edges in an n vertex complete graph is n minus 1 by 2. So n minus 1 by 2, let us see. This is our first, only one vertex. There is only one vertex. So in this graph, we see that n equal to 1. How many number of edges will be there? Let us put n equal to 1 here and n minus 1 by 2. So it will be 0. So there are no edges. Okay, this is fine for n equal to 1. For 2 vertices, let us see. We have n equal to 2. Place this value of n equal to n, which is 2, in this formula. It will be 1, and we can see that it is 1 only. Let us do it for 3 and then 4. So 3 we place, we find that the number of edges are 3 only. 1, 2, and 3. In a similar fashion for 4, we find 4 vertex, so the edges will be 6. So this is how we do it. And for 5 also likewise. N equal to 5 and n minus 1 by 2, place it, we have 10 nodes, 10 edges. Sorry. Next is the bubble sort algorithm is inefficient because it continues execution even after an array is sorted by performing unnecessary comparisons. Therefore, the number of comparison in the best and worst case are the same. We need to modify the algorithm in such a fashion that it will not make the next pass when the array is already sorted. How we are going to do it? This is the answer. So bubble sort continues execution even after an array is sorted. And if we want to prevent this unnecessary comparison, we need a Boolean variable, say which can be switched and initialize it by some true in the beginning. Along with this for loop, we add the condition if switch equal to this is switched, which we are taking as a Boolean value. We add the condition switch equal to true and make it false inside the outer for the loop. And if a swapping is made, the value of switch is made true. So if no swapping is done in the first pass, no more comparison will be done further and the program will exit. So bubble will be like this. We have an array and n numbers. So we do it exactly in the same way we do with the for loops for the bubble sort algorithm. We are aware of bubble sort algorithm. But we will introduce here with a Boolean value which is switched, which is equal to true right now. And when we pass, so if pass, we check for n minus 1 and also if switched equal to true, then only we go inside. And if we went inside, we'll make it false. And for the next pass, we will make it again true. And when it is true, we can go back and then check. So this true, here false and here true will make us believe and implement this algorithm such that there will be no extra comparison after or no extra inefficiency once the sorting is achieved. Okay, next is which sorting algorithm is easy adaptable to a singly linked list? Explain your answer. Let us see. So insertion sort is easily adaptable P to single linked list. So in this method, there is an array link of pointers, one for each of the original array elements. And initially, we take link I equal to I plus 1, where I lies between 0 and n minus 1, and link n minus 1 is initially minus 1. So the array can be thought of as a linear linked list pointed to an external pointer first, which is initialized to 0. To insert the kth element, the linked list is traversed until the proper position of xk is found, or until the end of the list is reached. So at that point, this xk can be inserted into the list by just merely adjusting the list pointer without shifting any elements in the array. So this reduces the time required for insertion, but not the time required for searching for the proper position. And the number of replacement of link array will be order of n. Sort the following sequence of keys using merge sort. So merge sort will be something like this. These are the values. We partition them. How we are going to partition them? First of all, pass 1 will be these values 66, 77. These are single values. We combine them. So we combine these two, 66 and 77, and the merge is 66, 77. For 1188 will be like this only. But for 22, 99, 22 will come here and 99 will go here. In this case, we have 33, 44, it will remain like this. 54 is a single element, no problem. And when we want to combine these four, again, 11 will come here, 66 will come here, 77 here, and 88 here. When we combine this, 22 in the first position, 33, then 44, and then 99. 55 will remain its position. Then we combine these two, say, lists we need to sort. We combine them and these will be sorted like this, and 55. Then we combine these two lists in the end. 55 will gain its position here. Now this is sorting using merge sort. Draw a B tree of order 3 for the following sequence of keys. How can we make the B tree? So the B tree will be something like this. And you need to follow that balanced tree condition that we start with 2, then we add here and there. Then we need to break it. We assume that the order is 3. So maximum of 2 will be taken, otherwise there will be reorientation or breakage of the node. So this is how we make it. Please try it yourself. So these are a few questions on data structure. We'll be taking more shortly. Till then, thank you so much. Take care.